Hello everyone, we're Group 18. Today we're going to introduce our Grab and Go robot. Next. Nowadays, because of increasing variety of grocery products, big box retail stores tend to pile things high up on shelves, and shopping could be unsatisfying when things are heavy and out of reach that customers have to ask for help from an assistant. It is also troublesome for elderly and disabled people. To solve the problem, we propose to build a retail store robot arm that fetches items and drops them in your shopping cart. With our robot, customers can get what they want easily and conveniently. For the prior research, Walmart have shelf scanning robot that search for out-of-place items with a beam of light. Moreover, warehouse robots are more commonly used for stock of goods in warehouse environments. However, due to limitations of function deficiency and high demand of space, both applications cannot achieve our goals. Next slide.
We would like our robot to be flexible enough to retrieve items from most places. So the design consists of 3 prismatic joints and 2 regular joints in the order of PRPRP for a total of 5 degrees of freedom. As the figure shows, the base frame is at the top nearing the ceiling. The black bar represents the axis of the prismatic joints, and the length is variable D1. It's basically parallel to the long shopping aisle. After an offset of D2, the second joint is rotated by an angle of θ2, allowing the robot to turn into or out of the page. Then we have another prismatic joint with a max length of 2 meters that enables the robot to move down. Finally, we have the last 2 joints to help the end effector to grab products from the shopping shelves. Once the coordinates are set up with right-hand rules, we can fill out the DH table, then the Jacobian matrix and forward kinematics can be calculated on the right. Next page.
On the right, we have our inverse kinematics of a 5 degrees of freedom robot manipulator. This is an important factor in calculating the position and orientation of our end effector. Here we show 2 different graphical representations of inverse kinematics to find the solutions. We find D1, D3, and D5, and then using that we calculate θ2 and θ4. On the left, we have our 3D CAD model of our robot that shows reaching the target position and then grabbing the product using a revolute and prismatic joint. After that, the robot uses its prismatic joint and revolute joint to drop the item to the shopping cart of the customers.
Okay, so for MATLAB trajectory simulation, we made some assumptions. First, we assume that the first prismatic joint has already been moved to the target position. So we only have to analyze motions from the 2nd to 5th joints of the robot. Some parameters are determined as well. The robot starts and ends at rest. The time for the move is 3 seconds for each phase. For phase 1, we set the coordination as 0.5 minus 0.5 for the initial position. And for the end position, we have 1 minus 1. This means the robot arm starts moving from the rest position to the target position to grab the product. For phase 2, we get to start at the end position of phase 1, then go to the end position of minus 0.5 minus 2. This means after the robot grabbing product, it goes to the shopping cart and drops the product into the cart. The pictures on the right side and effector positions and velocities versus time for phase 1 and phase 2.
To conclude, our Grab and Go robot arm should be capable of moving grocery from retail store shelves directly to your shopping cart. The robot arm is capable to fetch things in high or unreachable places for customers in a swift and efficient manner. A future extension installing an alternative robot hand that switches tools to grasp different shapes of products from grocery shelves. Adding a camera or sensor that can identify the product types and position more accurately. Programming and training the end effector to handle different packagings with corresponding weights. That's all. Thank you for listening.